it's time for us to deal with some definitions now. And before you turn me off, it's very important for us to be speaking the same language when we get into this chemistry. So bear with me for a couple minutes and we're going to define some very important terms for you. Okay, let's make sure that we understand the difference between atoms, molecules, and ions. Atoms, of course, are the individual elements in their indivisible form, at least using Dalton's postulate at least. Again, we're going to not worry about any type of a nuclear event, any kind of a nuclear reaction right now. So atoms would be our indivisible particles that we're going to be using, combining to make molecules. An example of molecule would be ammonia, water, carbon dioxide, sulfur trioxide. These are all, again, examples of molecules. Discrete packages of atoms connected together. Okay? Now again, what I mean is very well defined numbers of atoms connected together. And you'll notice that there is a defined ratio in this case of hydrogens to nitrogen, for instance, in the case of ammonia. Okay? That's going to be different than ionic salts or covalent lattices where we have an undefined number of atoms that are also stuck together, but there's no clear separation point about how do we describe this. We can talk about the ratio of one element to another, but there's no obvious breaking point. Examples of this would be sodium chloride or magnesium chloride, sand, silicon dioxide. So there's many types of materials where atoms are bound together like they are in molecules, but there's no clear separation point about what we want to call a molecule. So again, to differentiate here, we have lattices versus molecules, discrete packages of atoms versus infinite arrays. Again, as an analogy here, think of a brick wall, for instance. Many bricks stacked together. They're very ordered, but there's no clear separation point. Then finally there are ions, and what separates molecular ions or simple ions from molecules is simply that they have an overall charge. They can have an overall positive charge like the ammonium ion shown here, or they can have an overall negative charge like a chloride ion or a sulfate ion. If they're positive charge, we often use the term cation, indicating a positive charge, and a negative ion is called an anion, or again, a negatively charged ion. So once again, have clear in your mind the difference between the atoms, putting atoms together to make molecules, or putting atoms together to make lattices, and that different from all of those are ions that have an overall charge that's positive or negative. And once again, as far as ions go, we can have molecular ions, or we can have atomic ions. So chloride would be an example of a simple atomic ion. Ammonium would be an example of a molecular ion. Okay? Now, before I go on, let's think about molecules a little bit more and focus now more on molecules for a moment. Suppose that these beads correspond to a molecule of some kind. How do I describe that? How do I write on paper a description of this? There are many ways I could do it. I could draw a picture of what it looked like if I knew what the molecule looked like. But of course, 100 years ago or so, I may not have any idea of what the molecule actually looks like. All I know is the ratio. So how do I describe it? Do I describe it as 4 greens and 2 oranges? Or maybe I should simplify that idea and just say, well, the ratio is just 2 to 1. So maybe I should describe it as 2 green to 1 orange. Well, makes no difference whether I describe it as 1 to 2 or 2 to 4, unless I know for a fact that the molecule actually contains 4 greens and 2 oranges rather than 2 greens and 1 orange. Because that allows me to differentiate this molecule from this one. This also has a ratio of 2 to 1, just like this one, 2 greens to 1 orange, but they clearly, I can see, are different, and they're going to have different chemical and physical properties. They're completely different things. I'd like a way to describe these two things in such a way that I can write them on paper and indicate the fact that I've got a different molecule here than here. So I can use what's called a molecular formula to describe 4 greens to 2 oranges, and then its molecular formula would be different than this guy, which is 2 greens to 1 orange. Or I could just simply, if all I care about is the ratio, the simplest possible combining ratio, I would describe them both as a 2-to-1 ratio. That would be called an empirical formula. So let's define those two ideas. Again, a molecular formula shows the exact number of the atoms that are in a molecule. So for instance, the molecule benzene has per molecule 6 carbons and 6 hydrogens. Molecule water, something we're all familiar with, has 2 hydrogens to 1 oxygen. Now notice that if I was describing, I'll do these others too. Hydrogen peroxide, something that you can buy again at a drugstore for cuts, has a molecular formula of 2 hydrogens and 2 oxygens. Carbon dioxide, 1 carbon to 2 oxygens. And so this is how we would write it, the element followed by a subscript telling us the number of atoms that are being combined. The empirical formula, again, doesn't pay any attention to how many how many atoms are in the molecule. It only looks at the ratio of atoms within the molecule. So again, it shows relative amounts, underlying relative amounts of the atoms to be the simplest integer ratio. So benzene, although the molecule is 6 carbons and 6 hydrogens, the empirical formula would only be CH, 1-to-1 carbon and hydrogen. Water, however, would have the same empirical formula as it does molecular formula, because again, it's already deduced to its lowest integer ratio, 2 hydrogens to 1 oxygen. So the molecular empirical formula for water is exactly the same. Not so for hydrogen peroxide. Hydrogen peroxide's molecular formula would be 2 hydrogens and 2 oxygens, but again, its empirical formula, the ratio of hydrogen to oxygen, would only be 1-to-1 rather than 2-to-2. Carbon dioxide, on the other hand, like water, would have the same molecular and empirical formulas. Okay, you get the difference between those? Now, what about ionic materials, like we talked about, for instance, sodium chloride, where we can't easily define what a molecule is? Well, there's no choice here. We have to use the empirical formula to describe it. All we know is that there's a 1-to-1 ratio of sodium and chlorine. So we would always use the empirical formula to describe an ionic material. How do chemists represent molecules? Well, there are many, many different ways to represent a molecule. These are just some of the different ways. We can model them if we know what their shape is. This is a model, a 3-dimensional model of the molecule methane, 1 carbon and 4 hydrogens. This is a different type of molecule, of modeling. Again, chemists just love to be able to hold something and turn it and see it as if they could be on a microscopic level and actually see these molecules. So very often people will represent either with 3-dimensional models or sometimes, again, with a graphic picture that represents the molecule. So as an example, again, let's look at a molecule called cyclohexane. Cyclohexane, we'll see more about where this name comes from a little later. But for right now, I'll just tell you it's a ring of 6 carbons stuck together, and each carbon has 2 hydrogens coming off of it. So chemists can draw that molecule this way with simple lines connecting the atoms, indicating that those atoms are stuck together. This is a shorthand that organic chemists love to use. We'll talk more about that later. Organic chemists use carbon so much that they get lazy and stop writing the carbon, and it's just kind of the default. If nothing else, assume it's a carbon. And this is just a different way, again, to draw it. This is what's called a ball and stick representation of the same molecule. And you'll notice it doesn't look at all like this anymore. This is actually a closer representation of what the geometry of cyclohexane looks like. And again, we'll understand much, much more about the geometry of molecules later. Right now, don't worry at all about, don't let these pictures bother you. This is actually very much what the molecule would look like if you could see it on a molecular level. But can you predict that? No, there's no way you can predict it yet. But that's one of our goals, to be able to get to this point. No matter how we model it, though, one thing remains the same. Its molecular formula is always going to be C6H12. And so, will that formula uniquely define this molecule? The answer is no. So a molecular formula could describe many different molecules. It doesn't have to, but very often it can describe many different molecules, and we'll see that that's going to depend on how the atoms are arranged, and it also depends on what the geometry is, what the angles are between one bond and another. Those will all give us different materials, but they'll all have the same molecular formula. So finally, let's do an example of something that you'd be likely to see. This is an example of a molecule called nicotine, something that you've certainly heard of. Nicotine is in the news an awful lot. In this ball and stick representation, we have hydrogens in blue, nitrogens in this very dark purple color, and carbons in black. And it may be a little difficult for you to differentiate between the black and the purple, but let me just point out to you the purples here, and these other guys are black. And the task before us is to write the molecular formula for nicotine. All right, so all we need to do in this case is we have only 3 elements that are combined to make this, and we'll start out with carbon. And now we just simply want to count all the carbons in the molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total of 10 carbons in the nicotine molecule. And then we would count the number of hydrogens next by convention. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. And then finally our nitrogens. In the case of nitrogen, we have 2. So the molecular formula for nicotine would be C10H14N2, but the empirical formula of nicotine would only be C5H7N. So again, the difference between molecular formula and empirical formula. Now, once again, I want to leave you with this thought. This little formula is a nice, convenient way to represent this ugly mess of atoms, but it does not uniquely do so. There are many different molecules that have that exact same molecular formula. We call those molecules isomers of nicotine. They have the same number of atoms, but they're combined differently. So we'll have more to say about that very soon. For right now, the important take-home message here is that there's a molecular formula describing a molecule. There is an empirical formula that describes the molecule. The molecular formula gives us a much more accurate representation of what the molecule actually is, but it does not uniquely define it.